Right. So today we go to the second part of the hypothesis testing, and we'll be running some analysis. In particular, we'll be running t-tests and analysis of variance. So the files for today's lecture can be found on Teams and the Dropbox. There's an Excel file, there's a SPSS file. And I did manage to find out how to run some of the analysis on Excel. The good thing is that when it's run on Excel, you could, oh, people cannot find Excel file. I'm going to share it with you on. So the Excel file is to help us to understand the math going on behind these analyses. And also Excel is much more flexible than XPSS and running a lot of analysis. So me, myself, has been finding out these fascinating features about Excel. And even without the add-in that I mentioned earlier, that can actually allow you to do the analysis, Excel do contain all these functions that you can use to run the analysis, to get a p-value, for example. The other thing is that Excel is much more flexible in terms of handling the data. So if you manipulate data and moving it around and using formula to generate new data, Excel is much more easier than SPSS. So SPSS files, you can see that it has two files. There's a save file, that is the data, and SPS file is the syntax file. More on that later. Before we go into the analysis, I want to do a quick recap of these 4 steps that we mentioned before. The first step is to state a null and alternative hypothesis. The second step, now you can see it's a bit longer than before, is first of all, you need to decide what test you want to use, and you want to check the conditions for the test. We'll elaborate on that soon. And then, again, we turn our sample data into a test statistic. And then using the knowledge about the test statistics, the distribution of the test statistic, we can find a p-value. And then we can draw conclusions based on the p-value. In the previous lecture, we look at the case categorical independent variable and the categorical dependent variable. So step 1 will be stating the null hypothesis or the alternative hypothesis. And in this case, we have female and male answering, responding to a question in terms of selecting one of the 4 options. So the null hypothesis will be that when men and women did not respond differently to these 4 questions on these 4 options. And the alternative hypothesis is that they responded differently, or in other words, gender as a variable and the responses as the other independent variable, they're not independent of each other. We need to find the right test to check, and need to check the conditions to see if we can do these tests. And I've included some readings in the files about when to use about the chi-square test from McHugh. And from there, you can learn a little bit more about the test. So the general condition about running a chi-square test is, first of all, the level of measurement needs to be nominal, or in other words, categorical, or sometimes it can be ordinal. We haven't addressed the level of measurement issue yet, but ordinal is just quantitative data that only contains order information. So 3 is larger than 2, but not interval or not ratio yet. Okay, so ordinal data only contains information about order, but it's quantitative. Sample sizes of the groups are unequal. Okay, and or sometimes if you have quantitative data, but if one of the parametric assumptions have been violated, which I'm about to show you soon, then you can also turn those quantitative data into nominal data, okay, and run a chi-square test, which we know is a non-parametric test. That means that these tests do not have to, you don't need to meet all these parametric assumptions to run the test. So here are the conditions for chi-square test that I wasn't so sure of in a previous lecture, but now I've checked and it's more clear. So they should be counts, right? The levels of the variables should be mutually exclusive. So if you, which means that in our example here, if a male participant has selected didn't work from home and travel to work, he could not have selected other options. So these options are mutually exclusive. Each participant can only select one of the 4 options. That's what it means. Each participant or subject may contribute the data to one and only one cell, as I said earlier. The groups should be independent. So the 2 groups, male and female, they should be independent of each other. They should not be dependent in any way. And think about what that means, right? If they're couples, they're probably not independent. But let's not go into that, take that assumption for our data. And there are certain requirements about how many counts per cell should that be, right? So these are the conditions of chi-square test. It's quite simple. Now, and then the next step is to turn our data into test statistics. We've seen that through these equations, we basically get the chi-square statistics, which is by looking at equations, you kind of get the idea is it kind of addresses how much the observed count information deviates from the expected count count information from the data. And this general framework of depicting how the observed data deviates from the expected values is a theme that reoccurs a lot in our today's analysis as well. So the chi-square is actually connected to some of the analysis that we have seen today. So for the data we used, we've learned that how to produce the expected count value from the observed, but you can then using the row and column information to produce the expected, and then the chi-square basically summarizes how much the data to the left is deviating from data to the right. And the third step is to find a p-value. We've already discussed quite intensively what the p-value means. So here again, for the chi-square test, it's that the probability that the chi-square statistics would be equal to or more extreme than the one that we have observed in the data. So in our case, we learned that the p is smaller than 0.001, but then we can draw the conclusions. Because we have set the level of significance or the alpha rate at 0.05, so if p is 0.05, then we can choose to reject the null hypothesis and accept the alternative hypothesis that women and men responded differently in this question. So if you further look at the data, it seems that the women are more likely to not work or work from home than male. Okay. We briefly talk about type 1 error. So just a quick recap. So type 1 error happens when the null hypothesis is true, but we happen to observe an extreme value that is due to random chance. So if we observe the results fall out of the range, and when at the same time the null hypothesis is true, and then we have committed a false positive error, and the error rate is set before the analysis. So the error rate is usually is set at 0.05. So if it's a two-tailed test, it will share it at each end of the distribution. If it's a one-tailed test, then it's on a single end of the distribution. But the idea is that when there's no effect, we happen to find a very extreme value that suggests there is an effect. Okay? So then we will commit a type 1 error. We can also commit a type 2 error, but that's not what happened when we have found a significant result, right? So if the alternative hypothesis is true, but our data failed to detect this, then there's a false negative that will commit a type 2 error. Again, if we found a significant results, then we could not have committed a type 2 error. Right? But if we find a significant results, but if we, based on the results, we were to replicate the same study over and over again, for example, right? Then there's a likelihood of beta, as depicted in this graph, that in the future, there's a chance that if we run the same analysis, same study over and over again, when all the conditions are unchanged, there is this beta of likelihood of beta that we wouldn't be able to actually detect this true effect. If that's the case, then we would have committed a type 2 error. Okay? And 1 minus beta is statistical power, which means that how likely it is for the procedure for this to detect a true effect. Okay? So I hope that's clear. Right? If you found P is smaller than 0.05, then if you reject the null hypothesis, then you could not have committed a type 2 error. Type 2 error happens when you found a p-value that's larger than 0.05, but in fact there is an effect. We've briefly mentioned effect size. So here there's again I've included this in the revised slides for the previous lectures, but here it is again. Effect size means that it's a measure of the magnitude of a phenomenon. It could be a difference of means, so in this case, such as Cohen's d, or the strength of relationship between the two variables. Interestingly, Cohen said that effect size actually represents the degree to which the null hypothesis is false. Okay? So that's quite interesting. I can't really evaluate whether this is valid or not, but it's quite interesting ways to look at effect size. So we'll talk about effect size later when it comes to specific testing tests that we'll be running. We also see statistical power. We see how the increased sample size will increase the statistical power. In this case, the Cohen's d has been fixed. We're running a t-test between the two means, which we're about to show, which we will talk about in today's lecture. But if we have a sample size of 16 per group, then the power is quite low, only 27%. But if you keep the condition exactly the same and increase the sample size to 64, you see that now, first of all, the two t-values are, the two distributions that depicted there are further apart compared to the previous one. And the second is that now our power has increased. Now, the reason that the two distributions becomes further apart is because that the standard deviation or the standard error for these has been decreased due to the increase in the sample size. You can think of it that way, right? Roughly. So you can see that increasing sample size will improve our statistical power, so making our studies more likely to replicate. All right, so today we will talk about the case of categorical variable, the categorical independent variable determined on and a quantitative dependent variable. We'll look at t-tests, the rationale of the t-test and the formula behind the t-tests. And again, the Excel file is there to help you to understand some of the formulas. And we'll show you how to run two types of t-tests, first in Excel and then on SPSS. And then we will go to another case where so the t-test involves two means. And when you have more than two means, then you will have to engage in something called analysis of variance. We will look at the rationale behind analysis of variance. And we will look at a single the most simplest case is the single factor completely random design ANOVA. And if we have time, but I don't think we will have time to go to there. So if we have time, we will look at how we can have two factors, that is two independent variables in a completely random design. Okay? Before we go into specific analysis, we will talk about these assumptions, parametric assumptions. Now, because all the tests we'll be doing today are parametric tests, So these are assumptions about data that need to be met. Again, these applies to all the analysis, so I don't have to repeat them for each analysis. First of all, there has to be independent random sampling, which means that the samples are independently and randomly obtained from the populations of interest. And the second is normality, so the populations are each normally distributed. It's a little bit tricky about that. I'll elaborate on that in the next slide. And then also we need the homogeneity of variance, that the variances are equal in different populations that we're comparing. The homogeneity of variance, if it's violated, there are ways around it. So is normality. But often when these assumptions are violated, it's not that we cannot run these tests, but it's that our statistical power will be compromised in one way or another. So people still find a way to run these tests. As long as you're aware about these limits, you can still try to run these tests. But just to be aware that these are the assumptions about the data, parametric assumptions. So the normality is a bit tricky, and I've included a reading by Mordkov. I think he is the one that elaborated this issue the best, right? So remember, what we are testing in t-test and analysis of variance is sample means. And if you remember about sample means and sampling distribution, you will remember that there's the central limit theorem basically suggesting that the distribution of the sample mean will become normal if there's a sample size above 30, and that's regardless of the population's shape of distribution. So if we are talking about the sampling distribution, then it's always it should be normal most of the time if the sample size is sufficient. However, that's my understanding, but now I realize that if you look at what statisticians are saying, it is more complicated than that. So you should still try to check the normality of the sample data. So if the sample data looks like normally distributed, there are tests to test the distribution of the sample data against normality. So if it's not so deviant from normality, then you can say that you need 30 subjects per cell. But if the data you actually obtained from the sample severely deviant from normality, especially when it's strongly skewed, that is asymmetrical, okay, then we will actually need a higher number of sample size and per cell, like 100, okay? And it is possible that we will need some kind of transformation of the data, such as log transformation, to turn these data from non-normal distribution into a normal distribution. Okay, so this part is a bit vague. Like different people have different opinions about this. Some say I don't worry about this as long as there's central limit theorem, and the sample size is large enough. Some say that you should still try to check the normality of the sample data, and the CLT has its limits. Okay, but take a look at the Mordkov's reading that I have included in the folders to if you care about this issue. But the general rule of thumb is that you should check for normality and to make sure that your data is not too severely deviant from normality. So today this data, okay, so today the data is well, the studies and designs comes from, I'm using the project that I'm working at that is calling for accent bias and anti-bias intervention in the United Kingdom. So we have this accent bias Britain project. If you're interested in it, you can go and check out the project. So I'm not exactly using the data, but I'm using the materials, and I'm using the materials to come up with designs. The data you saw are not actual data from this project, but the data that I made up, okay? So, but since this is for teaching, and that would work. And also the materials are actually from the study, but the designs are also, I made up the designs just to illustrate a different kind of experimental designs and how can they influence the analysis that we're going to run. So a little bit background about this project. So we're interested in how accent leads to judgment and bias, a bias in judgment during the hiring decision making. So in linguistics and sociolinguistics and in both in psychology, there are theories that are suggesting that accents, especially regional accents in the UK, they serve as a cue to people's social background. And the social background can further trigger, can lead to the activation of stereotypes, which can lead to biased judgments about job candidates' competence during hiring, especially in the legal industry. So that's what our study was focusing on. It focused on how the legal industry look at evaluate candidates speaking in different regional accents in the UK. The accent that we are going to examine in today's lecture, we have 5 different accents, but I'm going to pick 2 of them for the sake of simplicity. One is called multicultural London English. It is a working class accent in London, especially in southeast London, that are popular with the people with ethnic minority backgrounds, such as African and the South Asian. Right? And then in contrast, we compare that to the Queen's English, or the received pronunciation. If there are linguists out there, you probably know it better. So it is the national standard, the BBC English, the upper middle classes. So let's say like we run a study that we want to see that does accent influence rating at all, right? And this is a simplest design. It's called a between subject experimental design. So the independent variable are the speakers. So we have 2 speakers, okay, assuming in this study. And the dependent variable is candidates rating. Participants will listen to a recording of one candidate, okay, because they got randomly assigned to one of the 2 conditions. Each condition contains a speaker of one accent. So they listen to only one candidate. And we made recordings of these their responses, short responses to interview questions, and we make recordings so each speaker make the same recordings, make recordings of the same scripts. So we have the 2 candidates speaking exactly the same, providing exactly the same answer, and hopefully that the only thing that differs from them is accent. We all know that's impossible because there's so many different linguistic information in the people's spoken speech. But let's assume, for the sake of simplicity, that's what we are aiming for. So the key is that this is a completely random assignment of participants into one of the 2 conditions. Okay, so each participant rated one candidate. The rated candidates on the employability. Again, there are multiple questions in our actual survey, but here let's just say that the employability is rated on a score from 1 to 10. And here are some samples about I want to show you how they sound like, actually. So let me just quickly see if I could pull out the Safari and try to play with you some of the. Okay, so the first one is. The first one recording is from the multicultural London English, and it is a response to the question. I don't know if you can see the question. What attracts you about working in law? Okay, so let me know if you can hear it.
Law is interesting, and I enjoyed my studies. I can't pretend that money isn't a factor. We all come out of university with significant debt, and a career in law allows a good quality of life and financial security. I'm also very interested in the international aspects of working in law. I've always dreamed of working in America, and this could be the first step towards international career experience too. I work hard, and I think my style of working will be suited to law and the type of international work that is done.
Okay, so that's his recording. And then this is a recording from a received pronunciation speaker of the same script. Okay.
Law is interesting, and I enjoyed my studies. I can't pretend that money isn't a factor. We all come out of university with significant debt, and a career in law allows a good quality of life and financial security. But I'm also very interested in the international aspects of working in law. I've always dreamed of working in America, and this could be the first step towards international career experience too. I work hard, and I think my style of working would be suited to law and the type of international work that is done.
Okay, so that's that. So now you get an idea. Like it's exactly the same scripts, but we have different speakers speaking in different accents. And in reality, we have about 100 of these recordings. I have 10 different questions, blah, blah, blah. 10 speakers, 10 questions, so 100 recordings. But here we're just using 2 of them. Okay, so any questions about the design or anything about the study? I assume I was clear. So let's state the hypothesis, right? The hypothesis really the null hypothesis. Who is doing the rating of employability? The participants. Participants are okay. Who the participants are? Well, the participants are either in our nationwide survey are the public, UK public. For our lawyers study, we use law firm HRs and lawyers who actually works in the corporate law firms in either London or Leeds. Okay. Now, so these are the hypotheses. So HO is that the population means of the rating for each candidate are identical. So mu1 equals mu2. Right? Again, these hypotheses about the population means. Okay. So the alternative hypotheses are that they are different. Some more questions apparently from the students. Do they have the same qualifications? We did mention that they have the same qualifications. They are applying for the job of an entry level solicitor. It's a trainee solicitor, so which means that they've all completed all their trainings, and there was a professional course they have to take before they were able to apply. So anyway, they've applied all the qualifications, but that's all what we have mentioned. So that's that. Okay. Right. So now the next step is to find the right test and find the right test and for check the conditions. The test we're going is the two-sample t-test. So the Fisher developed it in 1925. It's the same Fisher that developed the Z-test, I think. Oh, the null hypothesis significant testing paradigm. So the test is used to test the difference between 2 population means estimated from 2 independent samples. And there are some conditions. First of all, you need to meet a normality, and then you need a homogeneity of the variance. I'm not going to go too much into normality test. I'll show you later in this PSS, or perhaps in the next lecture, I'll show you how to do that. But for homogeneity of variance, it can be done in Excel, and it can be done in XPSS as well. And then we have we're assuming that we have independent samples. So that condition is also met. Okay, so this is a confusing bit. I hope you're not too scared from this. This is not too scary. The thing is that we need to turn the data into our t-statistics. And so first of all, let's take a look at the equations, and then we will see the data in Excel sheets to make sense of these equations. So the first equation shows that t equals the sample mean minus the population mean. So the difference between the differences. That's a little bit confusing. So let's put that for now. But the denominator is the standard error of the difference, right? So we need to calculate some kind of a standard error for the difference score. And that's the next equation shows that. And when the null hypothesis is true, because mu1 and mu2 are the same, and they kind of cancel each other out. So now we can see that the t-value is basically the test between the 2 sample means x1 bar minus x2 bar, okay, divided by what we call standard error of the difference, which is basically the standard variance, the standard the standard error for each sample mean pulled together, right? So as x1 bar squared plus x2 bar squared. Again, I know that's that's a little bit too much information. I'll show you how it's done in Excel sheet. But even all you have to know is that it's a pooled estimate of the standard error of the difference score between 2 sample means. Okay? So and to the right, you can see that if the variances are homogeneous, then you compute a pooled estimate of, first of all, the variance of pooled variance. So the pooled variance, if you look at it more carefully, that looks somewhat familiar, right? If you remember how the standard deviation is done, so this is quite similar to that. So in the first bit, you have x1 minus x1 bar squared, which means summed is the difference between the first group, the scores in the first group with the first group mean squared and sum, okay? And then you do that for the second group. You add them together, divided by n1 plus n2, which is the group size of each group, minus 2. So that's, you get the idea. It's a pooled estimate based on information from both groups. And then you put that SP squared into the formula underneath. Again, you pooled again because the two groups might have unequal sample size. So you kind of pull that again to produce the standard error of the difference. Now let me show you that in the Excel file, so we can make sense of how the data looks and how what the equations actually are implemented into the data. So if you look at the data, there are a Lecture7 t-test. There's paired sample t-test, which we'll leave for now for the next bit. So now this is the independent sample t-test. So here's our rating of speaker 1. That's the rating for speaker 2. Okay, so these are two columns indicated the two readings. Make it a little bit bigger. So remember the observations for speaker 1 and the scores for speaker 2 are from different participants. And that's something to keep in mind. That's why it's two independent samples, because they're from different people. There are less people scores for speaker 2 because there are only 9 participants for the second group. So this is just to show you that this independent sample t-test can be run with unequal sample size. So you can see that to the right-hand side, in the equation, you see n1 plus n2. I'm going to magnify that on the screen so you can see that n1 and n2 referring to the sample size in each group. So in this case, n1 is 10 because we have 10 observations, and n2 has 9. So then we can calculate the group means 5.2 and 7.11 and standard deviation for each group. In this case, we see that it seems like the second speaker 2's ratings are higher than speaker 1's ratings, right? But we need to test that. So the next equation, we have a test. Let me see if I move on. So the next step is to find out the p-value, right? So if you click on each cell, double click on the cell, it will reveal the equation that's being used. So this one, the one that's been highlighted right now, F-test, is the test of the equal variance. It basically, remember, one of the conditions for t-test is the variance needs to be equivalent across the two groups. So this tests that, right? So it's called the F-test because it is an F-test, but its formal name is called the Levine's test, right? And we'll see that in SPSS. It's more clear in SPSS than in here. So this one tests whether there's the variances are equal. So we want a p that's larger than 0.05, right? If p is smaller than 0.05 here, then it means that the variances are not equal. So we don't have homogeneity of variance. But a p is larger than 0.05, here it is, which means that the variance is equal across the two cells, across the two groups, okay? Now then we can go ahead to do the t-test itself. So this t-test, so this is a way that to directly obtain a p-value for the t-test. And that's the way that Excel does it. So basically it uses the function t.test, and the function takes the first array is the values from the first group. Second array is the value from the second group. Okay, and here are the two more parameters, 2 and 2. The first two indicates this is a two-tailed test. If you look at the two-tailed test, okay? And remember, because our hypothesis is that they will be different, instead of one is larger than another, we use the two-tailed test. The second two means that the type of test, the t-test that we're running. Okay, so the second two that I'm highlighting on the screen here, that indicates the type of t-test we're running. And this whole equation, this whole formula returns the p-value, okay? It directly returns the p-value. Now here are the three types of values that this argument, the type argument, can take. If you enter a 1, it will be a paired t-test. If you enter a 2, that is two sample equal variance. And if you enter a 3, it's a 2 sample unequal variance. Okay? So if our test of equal variance returns a significant results, then we have to use type 3. But because our p is larger than 0.05, we can use a type 2. Okay? So that gives us a t-test, which is p equals 0.0153. And that's good, right? Now we have the p-value. But for those of you who wants to report the results, we know that we need a little bit more than p-value. So we need so in this little form table underneath, I showed you how the t-test related statistics are being produced. And again, these are just the formula is like a bit more difficult to see, so you can figure it out on your own. But this S square is just SP square that I'm showing to the left on the PowerPoint. Okay, so basically that's the same equation. You can figure it out when you have time. I'm not going to go through the exact equation, but you can see that this basically is the differences of each score with the mean of those in the group, with the group mean squared and summed and then summed together and pooled. Okay, and that's the standard error, which is the lower part of the t equation showing to the left-hand side of the screen. Again, this is pooled because one group has a sample size of 10, the other group has a sample size of 9. Okay, that's the degree of freedom. Degree of freedom equals the sample size of both groups summed together minus 2, and that's our t-value. Okay, the t-value, that's how it's calculated. It's the equation to the left. Okay, so that's just how in Excel I've entered the equation. Now this p-value, I got it a little bit differently from the p-value above. This p-value uses some different functions called t-dist distribution, two-tailed. 2t indicates two-tailed. So it takes two arguments. The first is the value. The second is the degree of freedom. The degree of freedom here is 17. The value that we obtain is minus 2.7. But it only takes a positive value. So I have to use the absolute function to turn that into a positive value because it's a two-tailed test. So that p-value is the same, you can see, as the p-value that we obtained through the other method. So which means that these t statistic is about correct. Okay. The final shows that the Cohen's d. Now Cohen's d, as I'm showing in the PowerPoint to the left, Cohen's d is an effect size. Now, Cohen's d is the absolute difference between the two sample means, which is the same as the denominator of the t-value, but the denominator is the standard deviation, the pooled standard deviation instead of a pooled standard error. Okay, so there's a slight difference here. So I've also shown you that on the PowerPoint that it equals the t-value times square root of n1 plus the reverse of n2. So basically that's how it's calculated. So you would need a Cohen's d, the effect size calculator, in order to run a power analysis. Okay? So that's that. So if you have time, again, you can click on each of these cells to see how these the equations to the left is being implemented in Excel. You can double click and to show you the formula, and just press escape to zoom out. So if you have time, you can do that. So before we go to the break, so here, let me go back to the PowerPoint. So here is how the effect size can be interpreted, right? So as we said, D of 0.5 is a medium effect size, and D of 0.2 is a very large effect size. So in our example, we have a D of 1.24, so which means that the effect size here is very large. Before we go on a break, I would like to show you how to do this on SPSS. So if you have an SPSS open, you can have it open. I'm having a little bit troubles with my SPSS, so let's hope that it can actually work. But for SPSS, there are two ways of doing it, right? So about SPSS, the first is called the cloak method. It's a click and hope that the program can do what you want to do. So you click through it, and then you get the output. So this requires you to repeat the same procedure, click and hope procedure, every time you run the analysis. But the other method is called the syntax method, which means that you use cloak, but then you can save the syntax, okay? And then if you run the syntax over and over again, then that's much easier than having to click it over and over again, right? So that's two different ways of using SPSS. So we are trying to use the syntax way of doing it. So here it is. It has SPSS data file open. For those who are unfamiliar with SPSS, here how it looks. It has a data view and variable view at the bottom. But if you double click on any VAR up there, it switches between the two views. And you double click on the one named, it also switch back to the data view. Okay, so that's an easy way of switching between the two views. So right now the data is completely empty, but we're going to copy and paste the data into from the Excel file into SPSS so that we could do the analysis. So let's just copy and paste, right? Copy this observation to the second variable, right? And then you can see that's been copied. Now it has automatically created two variables. var 001 is empty. We're going to put the value of 1 into var 0001. Okay, so that's a categorical variable that indicates group membership. Now you can see that the data now is organized a little bit differently compared to in Excel, because in SPSS it's often organized in a way that's factorial. So there's a separate variable that indicates group membership. Okay. If you have all the variables in the hundreds, I don't know what that means. You should be able to just copy and paste. If you're having problems, then you can try to change the width and decimals. Oh, 400 instead of 4. I have no idea why that's the case. I don't know why. Like perhaps in Excel, you set it up in a way you need to check what in Excel. Check the format cells to see what exactly it means. I assume it has to do with set up the different computers when you use the decimal versus comma for the denominator of 100. So what you can do is that you can change these data in Excel into into some kind of into general, or like into a number with 0 decimal spaces. That might help. If you change that in Excel, that should be able to solve the problem. So that's that. But anyway, so let's copy and paste the second group there and call it 2, right? Okay, so the variable names are not very friendly because calling them var1 and var2. So you can double click on them to give them names. Let's call the first one just A. Speaker, just call it A. The second one, just call it BV. I mean, it really doesn't matter. I just want to keep it generic. And you can give it a label. say A is speaker. So label is what you use to, it's not a variable name. It wouldn't appear in the analysis, but just something for your convenience. You could actually choose to display certain variables according to labels. But let's just name it for our sake, call it evaluation. So we keep in mind, so it reminds us of what exactly those are. Okay, so that's our data right now. You can see that's a little bit organized a bit differently. So we have a categorical variable represented separately using 1 and 2 to represent the group memberships. And the dependent variable is now a single column instead of 2 columns. So we included in our Excel file. Okay. So the next thing, I'm going to run you through the PowerPoint slides. So now you can name the variables. The analysis you can find is you have to click Analyze, Compare Means, and Independent Sample t-test. Okay. So once you have been through that, and again, Analyze, Compare Means, Independent Sample t-test. Why don't I just put this on the side so that I can show you exactly what I'm doing. So here, actually the Analyze is behind Analyze. Compare Means one sample, independent sample t-test. And you can also see there are other options such as one sample t-test where you compare a single where you compare a single population mean to a set to a value, or paired sample t-test, which we're about to address in it later. Okay, but right now you just click on independent sample t-test. It give you this. If you give it pop out this this dialog, you will be putting in A into the grouping variables because that's what it is. You can drag it, or you can select it and click this send button. Okay, and then you can send a DV into test variables. Now, before you can do anything, you need to define the groups. So click on this to highlight the A and define groups. This is basically asking you which 2 groups do you want to test against each other in case you have more than 2 groups. So in this case, we only have 2 groups. We can enter 1 and 2. Okay, so and continue, and you can play around with other windows here. There's option window, but there's not much you can do here. You can see that it also will provide a confidence interval, bootstrap, which we're not going to go into now. But before you move on to OK, which would run the analysis for you, I would like you to click paste. So if you click paste, it will give you the syntax. So this is a syntax window. And if you want to run the analysis, you can just highlight the syntax and click run. Okay. You can also click run on top of the menu. That also can give you the option of run the selection. Okay. So always try to, if you just run a single analysis, just highlight this syntax and run the selection. Right? So if you run the selection, it will give you the outputs. Okay? So as you can see on top, it also repeats the syntax that you used to run the analysis. And there you go, you have the results. And this will going to quickly go over the results. And again, this is the syntax window. I just want to quickly go over the results before we go on the break. You can see that there are 2 rows. One is called equivariance assumed, the other called equivariance not assumed. The first one assumed the equivariance, but then it also runs the equivariance test for you. It's called the Levene's test. So you can see that it is an F test, and the significance value is 0.679. Okay, so it means that this is not significant. We can equivariance assumed is met. So that's our t-value, degree of freedom, and significance. You can see that when equivariance are not assumed, there's a different option, and then there's a different degrees of freedom estimated using some other methods. So if this significance of the Levene's test is less than 0.05, if the p-value is less than 0.05, then you have to look at the results of the second row, okay? Now, there's not much else to show you here. There's the mean difference, and there's the standard error of the difference. And you can compare these values to the values that we got earlier in the Excel, and you will see that they are identical. It also gives you 95% confidence intervals of the difference. So this means that the difference between these two populations range from minus 3.4 to minus 0.4 does not include 0, right? Which means that there is a difference between these two means. The first mean is smaller than the second mean. So that's it for the independent t-test, how to run it in Excel. We're going to take a break. We're going to come back in 10 past 2. There's some confusions about what values to put into the variables and how the variables are organized. Sorry if it was a little bit rushed. So here is a better view about what value is supposed to put in there. The second variable, var2, is the dependent variable. The first variable is the independent variable that indicates group membership. Remember in the Excel file, remember we have two groups. The first group is valued to speaker 1. Second group is valued to speaker 2, right? In the Excel file, those two groups are organized into 2 columns. But here we put them into a single column, in this case, the second variable. Now we need a separate variable to indicate group membership. So it depends on which values the second variable come from, you will need different values to indicate a group membership for the first variable. Okay? So in this case, as you can see, since when you copy and paste the second group into the SPSS, you have to give a different value for the group variable, which is 2. So now it becomes a variable with 2 different values. Okay, so 1 for the first group speaker and 2 for the second speaker 2. And we know that these 2 groups are from different participants, but we're not going to include a participant ID variable there to show that they're different participants. Right? So you can name them differently to make sure you remember what they mean. So A is speaker. So 1 is speaker 1, 2 is speaker 2. So that way it's easier to remember. And B, the second variable is called DV, and label it evaluation. Okay, I hope that's clear. I didn't really show you how to do the normality test, but I can show you now about how to do the normality to test the normality of the dependent variable, because remember we need some sort of normality test to make sure that our dependent variable is normally distributed. So allow me to navigate through this mess. It's okay, this is our data, okay, if you still remember. So for normality test, you go to Analyze, Descriptive Statistics, and Explore. Okay, Analyze, Descriptive Statistics, and Explore. And I don't know why they make it so complicated, but it's hidden somewhere. I don't know why they just could offer an option just run a normality test by itself, but it's hidden somewhere in Explore. So if you open Explore, you see a different, again, a different dialog window. And that's what I meant earlier. Like you have to click and hope, right? You click through this dialog windows and hope you get what you get. So now Explore, all you have to do is to send a DV into the dependent list. But before you click anything, you need to click on the thing called plots. Okay? Plots. In the plots, you have different options. You can have box plots, which is great. You can have stem and leaf histogram. You can have histogram if you want. Stem and leaf, let's just unclick that. No box plots. And then there's normality test with test. Normality plots with tests. So that's the thing that we're looking for. We click yes to that. Okay, so that's the normality test. And again, it's hidden somewhere. You click continue. You can choose to paste or you can just select OK. Let's see how what the syntax look like. And in my case, it's gone somewhere when I click paste. Okay, I've been having problem with SPSS since. Okay, window syntax. Okay, no, there's the syntax for that we just pasted. Select that, and it give you a bunch of results that explore the variable. Okay, so this is a summary of all the variables, and unfortunately on SPSS you cannot even zoom in to see what's in there to give you a better view. But there is the test of normality. Okay, so there's the Kolmogorov-Chernoff test, but the mostly used is called the Shapiro-Wilk test. So again, if it's not significant, which means the p-value is larger than 0.05, then it's not different from normality. Okay, so if it is significant, which means if the p-value is smaller than 0.05, then we'll look at how it deviates from normality. In the descriptives, you can also see skewness and kurtosis. These are also indicators of normality, but they don't give you any tests. So skewness is about symmetric versus asymmetrical in the distribution. Kurtosis is about the peaks. I'm not going to go into too much detail here. Here's a histogram. But yeah, the Shapiro-Wilk test is the test of normality. Okay? So again, where to find it is analyze, descriptive statistics, and explore. All right? So that's the SPSS for now. We'll come back to it later. And that's my cat wanting to go out again. So we can draw the conclusion since if you still remember, we got a p-values as smaller than 0.05. So we draw the conclusion that the population means that the ratings for each candidate are different. Okay? So that's our first problem. So the second study, again, this is completely hypothetical. And if some part it doesn't make sense to you, please bear with me. But assumably we can have a within subject design. We can have two conditions, but within subject means that each participant is exposed to each of the conditions. So in this case, which means that they will listen to both speakers and answering the exact same question in the exact same way. Again, if that doesn't make sense, just ignore that bit. But the key is that now we have participants listening to two candidates, right, instead of just one. So they make two ratings, one of the speaker one and one of the speaker two. Okay, let's assume that. Again, the results I'm presenting is completely fake. It's by no means like indicative of the actual findings we're getting. Okay, so the study actually the values in the data are completely irrelevant to the study. Okay, I'm just gonna let my cat out for a second. I'll be right back. All right, so the cat's out. Now let's go to the Excel file and look at the data for the paired t-test, okay? Or the paired sample t-test in its full name. So in the Excel file, if you scroll towards the right, you'll see that's the data for paired sample t-test. Now pay attention to how the data is organized here a little bit. So now, because we have each participant rated each speaker, we can have a participant variable that it makes sense to have, so these two values are from the same participants. Okay? So the values, the two values from the same row is from the same participant. Okay, so first of all, that's clear. Okay, in the independent sample t-test, it is not possible because these values are not from the same participants. So there's no pairing between these values. You can pair each of them. It doesn't make any sense. But here, you can now pair those two values from each speaker, and you can calculate a difference score between the two. You can have the same mean and standard deviation calculated for each speaker, but you can also have a mean of all the difference scores. So each participant has a difference score between the two speakers, and that's the mean of all the difference scores. And again, because these are just values, you can also calculate a standard deviation of all the difference scores. Okay? That's something that you can't do with an independent sample t-test. So this is paired because both observations are from the same participants, right? So you can pair them. And because it's paired, you can also calculate the correlation between these two variables, which we'll talk about in the next lecture. But the correlation here is using the Excel function correl, and it gives you a correlation of 0.44, indicating these two are correlated. Right? So that's the assumption about paired t-test, which I'm showing up on the screen. So you have independent random sampling, you have normality, but in this case, you don't need to have assumption about homogeneity of variance. And the hypothesis is a little bit different. It suggests that the null hypothesis can be written as the difference between mu d is the difference, the mean difference score is 0. Okay. The alternative hypothesis can be written as, let me just correct that really quickly because that should be an equal instead of a unequal. Now the alternative hypothesis is that the difference score is different from 0. So in effect, the paired t-test, once you've calculated the difference score between the two speakers for each participant, it becomes, in effect, a test of the difference score against 0. Does that make sense? Okay. Instead of saying that it is a test between the two means, it is a test of the difference between those two means against 0. Which means that the t-statistics that is shown on the PowerPoint slides here the t-statistics is the d divided by the standard error of the difference score. So SD, so the SD here presented on the screen is the standard deviation of the difference score. Okay? And again, is SD divided by the square root of n is the standard error for the difference score, and that's the mean difference score. All right? And that simplifies things much more than the independent t-test, right? So it's much more convenient, actually, if other issues are not involved. So the Cohen's d is the difference between the two means divided by the standard deviation, not standard error, and that's the connection with the t-value. So since we have the difference, mean difference here, and have the standard deviation here, we can easily calculate the t-statistics using, once we have known the standard error of the mean difference. In this case, it's just the standard deviation divided by the square root of the sample size, and we know the degree of freedom. We have the t-value here. Again, it's much easier because we're basically testing this value against 0, the mean difference score against 0, right? And that's our p-value, and that's our Cohen's d. based on the equations shown on in the equations on the PowerPoint slides. Okay, so that's how it's done. Again, you can figure this out at your own pace at home. But the key is that you can notice that the p-value that we got is larger than 0.05. In this case, it's not significant, so we cannot reject the null hypothesis. But you can also notice that the coherence D is 0.64. So that's larger than a median effect size. So in this case, we have somewhat meaningful effect size, but not significant result. And if you want, you can try to run it through the G-power analysis using the G-power software program to see what kind of what's the sample size that's required to obtain a p-value that's significant. Right? Okay, I'm not going to run the paired t-test in SPSS due to the time limits, but in order it's located in the same area that I've shown earlier, compare means. Then you have paired sample t-test. Okay, so if you want, you can work it out on your own pace. Actually, let me just show you what it looks like. Dialog looks like this. So you have to use this little button to make a pair. Okay, so to indicate which two variables are paired. In fact, since we already come this far, why don't we just do it by just copy and paste this into the data. The data we had before, we just delete it. I'm just going to delete it. You can save it if you want. But now that's our new data. We have some empty cells we want to clear. Okay, so make sure there's no empty cells underneath. So now we have this data. We know the first one is called participant ID, right? So it's PID, we'll call it PID. The second variable is called speaker 1. The third variable is speaker 2. So now, before we move on, let's look at the structure of the data and see what it means. Now, instead of having a group variable, we have two separate variables to indicate that what I say, that the two observations from the same participant. And it is paired in the sense that it's locked in a row, so that if you sort the data in any way, if you sort PID, if you change PID in any way, it will also sort speaker 1 and speaker 2. So these are cooped together, right? Locked. You see there's no group membership here, okay? Because we only have one group, and the whole group going through these two conditions. Right? So if you want to run the analysis, you can go to Analyze, Compare Means, and Paired Sample t-test instead of Independent Sample t-test. Okay? Just click on that. It pops out this Paired Sample t-test window. So now you have to build this pair. You need to move the first variable into the pair by just moving it into the pair. And then you have to click the second one and move it into the pair. So now you have a pair of variables. And I'm again having problem with my SPSS. I don't know what's going on. I cannot click OK for whatever reason. But I should be able to. Okay, so I have to restart my SPSS, which is really not convenient. I'm going to pause. So let's first deal with a single factor factorial design. Okay. The factorial means that we're treating the independent variable as a factor. Okay? And the factor has different levels. Okay? So let's say that we, in our accent bias study, we are still running a between subject design. Now the independent variable now is called intervention. What I mean by intervention is the intervention to reduce people's bias. And again, don't ask me if there's a bias or not. It's complicated. That's for the sake of this study, for demonstration. Let's say that we want to find the best intervention that can be quickly used by human resources to reduce the bias, accent bias. So now participants are randomly assigned to one of 4 conditions now, instead of just 2 conditions. Now we have 4 groups. So they first went through a very quick intervention, and then we assume that they listened to a recording of one single candidate. And let's say this candidate speaks BBC English, received pronunciation, okay? And then they will make the speaker evaluation. So our dependent variable is candidate rating, independent variable is the intervention. So these are the anti-bias intervention that we came up with. There are the 3 interventions, and the 4th group as a control group without any intervention. And the first 3 interventions are raising awareness, ignoring accent, or committing to objectivity. What I mean by intervention is just like a simple instruction asking people what to do. So the raising awareness one, I'm just basically telling people, hey, before you evaluate this candidate's performance, we just want to let you know that interviews in the UK can be influenced by the accent. And we actually specify what it means that candidates who speak with a standard accent will be rated more favorably than candidates who speak non-standard accents. And this is the accent bias. So please keep in mind when you are evaluating the participants, evaluating the candidates. So we told this to UK publics. Actually, we use an online sample. So there's people who are doing this online. They see this. This is one of the interventions. So I have 3 different interventions. The second bit intervention is called ignoring the accent. We're telling them to, whenever they hear an accent, they should focus on the content of what they actually talking about, and try to not pay attention to accent at all. Ignore accent, pay attention to what they're saying, right? Because that's if there's no bias, people should be completely judged based on the content of the response, instead of based on any kind of irrelevant cues. The third intervention is called committing to objectivity. We ask people that please make sure that you will be fair. Please indicate that you will be fair to the candidates. Another way of committing to objectivity is to tell them that your evaluation will be looked at by some experts, something like that. Okay. So again, the participants are randomly assigned into one of the conditions. So therefore, it's called a between subject design. So any questions before we move on? If there's, well, good. So, okay. So again, we're just following the 4 steps of hypothesis testing. The first step is to state a hypothesis. Here, the hypothesis is a little bit different from the t-test. Now you have 4 population means, which means one intervention is assuming there's a population behind this intervention, which means everybody have all the subjects in the population have taken the intervention, right? So that's completely hypothetical. This is a hypothetical population, because you can't have, I don't know, the entire human race to take this intervention. But we're assuming that there's a population behind the sample. Alternative hypothesis is a little bit tricky to understand. For the analysis of variance, it only says that overall, the population means are a little bit different. It doesn't really specify how they're different, but the alternative hypothesis is that the overall, you can detect a difference across these 4 intervention groups. Okay, I'm going to elaborate on that soon. So for this study, since the fourth group is a control group, then we can make a more specific alternative hypothesis saying that each of the first three groups are different from the fourth group. Okay? But you can also say that sometimes you're interested in which intervention is more effective. Then yeah, you can look at the other group 1 compared to group 1 to group 2 as well. Now, find the analysis and the test. The analysis we'll be running is called analysis of the variance. But basically, what it does is that the means are the group means, whether they are more variable than can be reasonably attributed to chance. This is being done through translating data into a test statistics called the F ratio. The F ratio is a ratio. As you can see, there's a numerator and a denominator. It is basically, as you can see from this is not a mathematical equation, but it's more like a technical, conceptual equation. So it is basically comparing the variation among the sample means, which is the group means, to the variation within the groups. In this case, any variation that happens within the groups are considered as random. And the variation across the groups is the variation caused by the intervention. Is the variation caused by the independent variable, in other words. Okay? And this is the F ratio. Okay? So again, this suggests that in our design, which is a completely random between subjects single factor design, the variations can be broken down into two kind of variations. One is the variation among the group means. So this is more systematic, and this happens due to experimental treatment, right? The treatment, if you know what I mean. So in the original, in the medical research, and I think that, which is what these analyses are developed for, they call it treatment. Right? In our case, treatment are these different interventions. And then there's the variance coming from within groups due to the random individual differences between participants or due to random measurement error. Now, because we randomly assign participants into these groups, we can say that any individual differences are actually random. Okay? And there's also, if you remember, the scores are always determined by different sources, right? So measurement error can also play a role, and we're also assuming that measurement error is somewhat random. Okay? So that's what happened within each group. So what means here, what the F test does is that it compares the degree of these two variances or variation, right? So by putting if you remember the equations here, there's again, so putting the variation, pitting the variation among sample means against the variation within the groups. Okay, so there's a ratio. So the ratio shows here is that if we have, in this case, we see there's 3 samples, assuming that there are 3 groups. And you can see that the sample mean indicated by the red dots, they seems to be different from each other, which indicates there might be something systematic going on. There might be some treatment effect, let's put it that way. But there's also the scores within each group also tend to vary quite a lot. So in this case, if the variation within groups is quite large in comparison to the variation between the groups, then it becomes the case that the ratio becomes so small that the variation among the group means becomes negligible, right? So in this case, the data will provide very little evidence against our null hypothesis. If, in this case, you can see the mean seems to be different, but more importantly, the variation as compared to the variation within each group compared to the variation of those 3 dots indicating the group means, seems to be, it seems like in this case, the variation among the group means would dominate over the variation within each groups, right? If this is the case, then the data will provide stronger evidence against null hypothesis. Okay, I hope that makes sense, right? So, and because I'm going to show you a bunch of equations that look like including sums, that could be quite confusing. Let's take a recap at what exactly is variance. So variance is a way of quantifying variation within a group of data. And so remember, standard deviation is the average distance between the scores and the data. Okay, between the scores and the data and the mean x bar, right? So if you have these data xi, and that's the mean, and you have the distance, and you can calculate the average distance, but you first have to square the distances. So because some of the distances are below 0, by squaring them, you turn all the values into positive, and then you can sum them up. Remember that, right? So you create a distance score, and then you have to first of all square them, and then you sum them together, right? So this is called sum of squares. Okay, there's a term for this. It's called sum of squares. It is a sum of all the squares. Square of what? Square of differences. Okay? This mean, right, can have different. You can have different means in the data. In our data, you have 4 groups. So the mean can either be the group mean, or it could be the mean across the entire data set, which we will call the grand mean. Okay, that's also something to keep in mind. Now, again, we're talking about standard deviation here, right? So now the standard deviation S is simply the squared difference scores, sum of squared difference scores divided by n-1 and square root. But you can also remember that the thing variance is simply the squared of the standard deviation, which is basically that. So it's a sum of squares, okay, divided by n-1, which is, in this case, the number of data points minus 1. But in the broader sense, this is called the degree of freedom. The -1 indicates that you take away 1 degree of freedom because the mean is set, right? If you set the mean, if the mean is already known, so the mean would take away 1 degree of freedom, okay? Which means that if you know 7 of the 8 scores in this data set and the mean, the last one, the 8th one, does not matter. So that takes away 1 degree of freedom, okay? I hope that makes sense. So again, this is the equation for variance, right? Again, it's a sum of square divided by n-1, which is degree of freedom. This is a very generic equation of variance that we will actually use in the analysis of variance. Now let's move on to the data in Excel. It's in a spreadsheet called ANOVA, and I'm about to show it on the screen. Okay. Let's just close that for now. Okay, so this is our Excel file. Earlier we had the t-test, but now let's move on to single factor ANOVA. So this is data I want to bring into attention. A1, A2, A3, A4 represent our 4 different groups. A1 to 3 are the experimental groups that have interventions. A4 is the control group that has no intervention. Underneath it is the group means. Again, our hypothesis is basically that these 4 group means in the population are the same. Okay? And the null hypothesis is that they are different. there are two things that I want to bring you to attention. First of all, we are assuming equal sample size of 8 for each group. This is quite important for a lot of reasons. Basically, you want to have relatively equal sample size, if not exactly equal sample sizes for each cells. If the sample size are not equal, then a lot of things analysis would have different results. It becomes a little bit difficult to deal with. Okay, that's why you try to make sure that the sample sizes for each cell or each group are as similar as possible. There is what I mean called the grand mean. The grand mean can be understood in two ways. First of all, is the average of all the data points, all the observed scores. If you calculate average, and actually you can see that at the bottom, Excel actually, every time you select these values, they tell you what the average is. That's the average. Right? It is also, because we have equal sample size across the 4 groups, it is also the means of the group means. So if you select the 4 group means, the average is also 4.25. And it is only the case when we have equal sample sizes in these 4 groups. All right? Moving on to the right, we have table 2. What table 2 does, these values in table 2, if you double click on it, you can see what it means, is the squared differences between the individual scores and their group means. Okay? And their group means. So that's the key bit. So the first value, 1, is the difference between A1 and the group mean. If you double click, actually shows you where does it come from. It's the difference between A1 and the group mean. Okay? So for this value, it uses the group mean for A2. For values in A3, it uses the group mean for A3. So again, we first calculate the difference and then we square them. Okay, if you look closely into the equation, you will notice that we first calculate the difference and then we square them. So these values are, if you compare it to what we saw earlier, is the sum of squares, right? It hasn't been summed yet. Okay, it hasn't been summed yet, but it's the squared difference. Okay? Moving on over. On table 3, we have the square differences between the individual means, but in this case, and the grand mean. In this case, if we double click on the value, you will see that the difference score is calculated between B4 and the grand mean. And that's for all the every cases here, they use the grand mean as the calculated difference between the scores and the grand mean. Okay? And here you can also have the variances of within each group. Okay? So these are variances already has been divided. You can see that the variances within each group is the sum of all these values, the squared differences within each group, divided by sample size within each group minus 1. Okay? So that's the variance within each group. So these are also can be calculated, and that's the variance within the average of these variances within the entire sample, within the whole sample. Okay. Actually, let's call it the whole data set, because sample refers to each group. So you have 4 samples, but the entire data set. So let's leave that for now, because this will make more sense if I show you the equations that are producing we are dealing with here. Right? A different way of looking at this is that each of the score that we saw in that table, in the observation scores, can be defined using 3 components. So XAI here is the each individual scores. That is the score that I've just showed you. So these scores, each of these scores, can be depicted using 3 components. The first component, mu, is the grand mean in the population. The second component, alpha A, is the effect of treatment A, which is the mu A, which is the group mean, minus the grand mean. And the third component is the random error, which is the score minus the group mean. Okay, that is considered a random error in this particular design. That's how we model error. Okay. So each score can be, so the variance of the scores can also be teased apart, right, to 2 sources. One is the variance caused by the treatment. The second is the random variance. Okay. So here are the formula that how they break down these variances, right? The first source of variation is the source A. A is our intervention here, right? So we can calculate the sum of squares in terms of the difference between XA bar is the group means with the grand mean. And then we can sum it up across all the levels of A. Okay, again, different score squared and sum it up, and then we have to time it by n, okay, to generate the sum of squares for A. This represents the variation in some way, the variation of group means around the grand means, because basically this is produced by subtracting group means from the grand mean from the group means. Okay? The second source of variation, we can have variation within each group around each of their group means. So you can see that you are subtracting the group means from each individual observation scores, and you first and square them. You sum up first within the group from 1 to n, and then across all the groups. Okay? So that's a sum of squares again, right? Sum of square of differences, but it's important to pay attention what exactly is producing these differences. Here, the difference is between each individual scores with their group means. We can also have the total variation, which is the variation of scores, each individual scores around the grand mean. So here, the variation is modeled by subtracting the grand mean, not the group means, from the observation, squared and summed it up within each group, and then between across the groups. And if we look at our Excel file, and they have already been calculated for you. The sum of squares, if you look at the table, so this is the sum of squared SS for A, right? If you look at the equation here, it is basically comparing, I'll make it a bit bigger. You can see these are the numbers of group means, subtract the grand mean, squared, and sum times 8. Okay, 8 is the number of observations in each group. So that is the equation to here, right? In Excel, source A. So that's how it's implemented. Degrees of freedom is 4 minus 1. We have 4 levels of A. A minus 1 is the degree of freedom for A. Now we have the mean square here. It's basically the sum of square divided by degree of freedom. That's for A. The second is the variation within each group. Here is called the error, or subject nested within A. So this slash here suggests that it's nested. nested means that each subject is exclusive to one conditions of A. This sum of squares is basically sum of all the values in table 2. Okay? Remember, table 2 is the square differences between individual scores and their group means. Hence, in our equation, in our PowerPoint equation, it is this bit. Okay? So that's sum of differences. That's square differences. Now, you sum them. If you sum them across the column and across rows, you're basically, effectively, we are summing them across the rows first and then across columns, right? So this is just the sum of all the values in table 2, okay? So the sum of square for error is just sum of all the values in table 2. Degree of freedom is 4 times A minus 1, is 8 minus 1, okay? 4 is the level of intervention, level of groups we have, and 8 is the number of observation in each group. Then divided that, we get the mean square for error. The total amount of variance is the total variance that is shown on the equation in the PowerPoint. It is all the values in sum of all the values in table 3. If you remember, the table 3 is the square difference between individual scores and the grand mean, which is exactly what the equation in the third equation total says on before it's summed up, right? And the two sigmas just sum up all of them across, first of all, across 1 to n, and then across 1 to a, 1 to 4. So 8 rows, 4 columns, sum them up. So these summed up to 110. Okay, coming back, 110. You'll notice that these scores, they're actually coming from different sources, but that 49 and 61 add up to 110. So which means we're basically breaking down the total sum of squares, indicating the total degree of variance within the whole data set into 2 components. One is the source of variance due to A, the other is error. Okay? That's it. By analysis of variance, we're basically breaking the variance, the total variance indicated here, into variance coming from different components, systematic or random. And then by using degree of freedom, we convert them into mean squares. And the F-test, as to the right, you can see, the F-test is basically the F ratio. The value of the F-test, the value that we're obtaining is F ratio, is basically dividing the mean square for A by mean square of error. That's it. Okay? If you look at this, if you double click, you can see those are the 2 values that are using. And then we can obtain the p-value by using this function called F distribution right-tailed. Okay, so using this value and get the right-tailed. I see some questions there. We're going to a break very soon. Why does the group equal 6? I thought that would be 4. Yeah, 825. 825. Degree of freedom for A equals A minus 1. It should be 3. A number of group. Oh, did I say 6? Sorry, it should be 4. Thank you for spotting the mistake. Okay, we're going to quickly move on. There's something called proportional variance. It's called eta squared. Eta squared. Put a D there. Eta squared. It is basically, in our case, dividing the sum of squares for A by the total sum of squares. Okay? In this case, eta squared equals 0.45, indicates that factor A, has explained 45% of the variance in this whole sample, okay? This whole group, data set. And cocons F is a little bit more complicated. It's a cocons F is the indicator of effector size. Now, in this particular case, it equals eta squared divided by 1 minus eta squared, and then square root. But that's not the case when you have unequal sample size. So it gets a little bit more complicated, but it can be estimated using G power, using the eta, once you have known the eta squared. Okay? Just know that cocons F is estimated from eta squared in this case because we have equal sample size. All right, so we have the p-value, we have the tested statistics, p-value, and we have some effector size measure. So now we have to find the p-value. By doing that, we can do that in SPSS. We're going to do that after the break. Let's go for a break for 10 minutes. I'm going to stop the recording. Okay, so now I'm going to run the analysis of variance in SPSS. How do you find SPSS, by the way? I mean, for those who are first time using it. I used to use just SPSS, but to a certain point where I realized that SPSS is actually limiting my learning and knowledge about statistics, because it is convenient in a way that it provides you with, like for those who are first-time users of any kind of statistical software, you can actually click through these windows and menus and get analysis done. But it is a software that made in the 1990s, and the entire interface has stayed that way. And it's clearly the way it interacts and the way you can use it is clearly out of date. I mean, we're in 2020 now. For one reason, for example, each data file has to take a new window instead of just can have like in Excel as a spreadsheet, because they needed this dual window mode for a dual view mode. They have a data view and they have a variable view. And also, if you start to work with SPSS a little bit and started trying to get into the results, the output that they gave you, you would just find out that it's almost impossible to get any values out of the output. And it will be faster in a lot of the cases, to actually read and type it into, let's say that you want to write a paper, you want to quickly copy that table from SPSS to your Word document. It's not that easy. And they made it so that it's extremely complicated. And also the graphs is just horrible. Like the graph is just the worst. So as you learn more about statistics, you know that you would need, first of all, flexibility. And second of all, you want easy access to all the kind of output that it produces. So either in text or in some kind of table that's already formatted for you, that you can just easily use in your Word document, because that's what you will use to write your report most of the time, or some other programs, which means that it needs to have like a very easy interface with other programs, and SPSS just don't have that. Not to mention that if you want to find help about SPSS, say you want to find help in syntax, and any kind of open sourced statistical package such as R, it's very easy to find help. All you have to do is just type, say you want to find help about a function named, I don't know, like about a function. All you have to do is just type that function into Google, the name of the function into Google, and the first result is usually the help, like that elaborates what the function can do, right? Not for SPSS. If you want to find help about SPSS, you're going to navigate through this IBM. First of all, Google wouldn't give you the results right away. It gives you a direction, either some third parties, right? So people have come up with like teachings about SPSS. That's good. But you would assume that IBM, which is the owner of SPSS, would have some kind of a tutorial available out there, right? And that's easily accessible. And you can find anything, any kind of a syntax, any kind of a question you have, all you have to do is just type and search. But no, like I've been through IBM like SPSS help page, it's just horrendous. I mean, it has all the information, but to find those information, you have to navigate, you have to search through the different versions of SPSS and then to find these tutorials hidden there somewhere. And mostly what you found out when you go to IBM is that they want you to pay them, they want you to buy their product, and they care more about enterprise users. Well, a lot of enterprise still use SPSS probably. They don't give a shit about individual users that like our PhD students who like run analysis or who are learning these analysis. So it's also very difficult so it makes it more difficult for you to learn and to progress. But anyway, so for the ANOVA, there are two ways of doing it in SPSS. So here are the name of those two. One is called GLM, which stands for General Linear Models Univariate. General linear model is basically regression models that can be used for any kind of analysis, such as analysis of variance. So this will give you eta squares and power if you ask for them. And it also permits test of means, which I will talk about later. There's also another program called One Way. You will notice that this is at the end of the analysis of means that you saw earlier. You see independent sample t-test, paired sample t-test, and then there's One Way. So One Way will also do very single factor analysis. You cannot have more than one factor. And it will do analysis of variance and give you tests of means if requested, but it wouldn't give you eta square, it wouldn't give you power. Okay. So we're going to do it in the univariate. You can also do it via syntax. If you open that syntax. Or you can also, but here I'm going to show you how to click through this analysis and find the analysis you need. So the analysis is located on Analyze GLM Univariates, which I'm going to put on the screen. That's my SPSS here. We'll set it to the right. So this is our data. You'll notice that the data looks again a little bit different from the data we saw on Excel, which I'm going to put up here. In Excel, we just simply have 4 columns. Each column is a group. But here we have combined all these columns into a single variable or a single column. And then we use this variable called A to indicate membership to the groups. Okay. Again, to the right, you have the Excel data file. And to the left, you have the SPSS. So SPSS treat A as a factor, right? So it's and the A is a categorical variable. 1, 2, 3, and 4 indicates group membership. So these are the same values that from the Excel. And I have a variable called B. Let's just put there. This is for if you want in some cases there are more than one independent variable. So this indicates that there's another independent variable there, which if we have time, we'll come to. But if you don't have time, we'll just leave it to the next lecture. And then it's always a good idea to have a participant ID variable. So if you sort the data in any way or delete any data, you have some kind of record about whose data it is, which data have you deleted. So PID is just from 1 to 38, indicating 32 different participants. So each group, you can see each group A, group 1, A2 have 8 participants, A3 had 8 participants. Within each group, you have 2 different B. So B, I think here is the interview question, assuming that you have the speaker doing different interview questions, right? But we're not going to come to that for this analysis just yet. Let's just treat this as a single factor design, because if you have another factor, it's called a 2-factor design. Right? So let's just treat it as a single factor design for now and run our analysis. So you go to Analyze, and you go to General Linear Model, not Generalized Linear Models. I know how confusing it is. But for Generalized Linear Model, you only have like very few options. If you go to General Linear Model, you have 4 options actually: univariate, multivariate, repeated measures. And we will click univariate. So this pops out. Now there are a couple of things here. Dependent variable is our dependent variable, the evaluation of the speaker. Okay. Fixed factors, random factors. What do they mean? Fixed factors is just the factors that are independent variables. We're not going to go into random factors because it's a little bit advanced topic that about how fixed effect and random effect are defined. Let's for now just say that we are going to use fixed factors. Covariates, we're going to leave that for now. But this means that you can include another continuous variable to control for the variance caused by that quantitative variable. Okay? So say you have a personality variable. You measure the personality, some kind of a personality, or let's say you have a political view variable, like a questionnaire about people's conservative versus liberal political views. And that's a questionnaire, and it gives a score that is quantitative for each participant across the entire data set. You can use that as a covariate to control for how the political view has affected the evaluation of the speaker. Okay. W as weight, I've never used that, just leave it for now. So remember, we're interested in how A influences dV. So we're just going to put the dV into dependent variable and A into fixed factors. Before we move on, let's check out these options to the right. The first one is called model. See that you can specify the model. Now it's full factorial. If you have more than 1 factors, you can start to build different models. But full factorial just means that all the independent variables are included. All the possible interactions between multiple independent variables are also included. There's something called sum of squares. You can say a type 1, 2, 3. The default is called type 3. I'm going to talk, if I have time, I'll talk about that in the future lecture. But right now, let's just say the default is type 3. And if in the future, if you encounter this kind of a sum of squares in any other statistical programs, you should be aware there's at least 1, 2, 3, type 1, 2, 3. And the default is usually type 3 sum of squares. Or in some program, it's called type 3 analysis of variance. Here it says include intercept in model. Intercept in the general linear model, in this sense, the intercept will be the grad mean. Okay. If you don't include intercept, it just doesn't show the results. Show the intercept in the results. And because this is a linear model, it will have an intercept. Right? The second one is called contrasts, which is actually quite confusing. So we're not going to look at it for now. So plots gives you the plots of mean plots. But again, SPSS just is so bad in terms of plotting. You would rather just use the means and plot it in Excel. Post-hoc, okay, which means that you can conduct some kind of post-hoc contrast of means. So if you want to compare the specific means, compare between two specific means in the among these levels of A, you can use that. But we're not going to use it for now. We're going to use a more simpler way to do it through the syntax. But if you just if you select it, you can see that there are different methods of conducting these tests, which we will come to later. So right now, let's just leave it be. You can save the certain values, leave it for now. And now, but the options is the one that we'll play with a little bit, right? So for options, you can see that there are different things that you can do here. You can ask for descriptive statistics. Right, let's put A here first, right? Display A for means for A, and you can have display descriptive statistics. Click homogeneity tests, which you test the homogeneity of variance. So click that. Estimates of effect size, which it actually gives you the eta square, which is not really effect size as Cohen would define it. Let's just ask for that eta square, and also it will ask you it can give you observed power. So based on the effect size and your sample size, how much power you have for this particular study. Let's just click those 4 and continue. And at this point, you can say, okay, but let's just use paste again to have our syntax. Right, so this syntax is also available in the syntax file that I've shared. So you can see that what the syntax means, right? Union ANOVA is the method. DV is dependent variable by A, right? So in the future, if you started to get familiar with the syntax, you can directly edit the syntax to get the analysis that you want. So method SS type 3, remember this sum of square, type of sum of square. This is using type 3. Include intercept. So these are the arguments. EM means, this is a very important command. So slash EM means. This came out because we asked for displays means for A, but we can do so many things with EM means that we're just going to show you later. Okay. Right now, just leave it as print. You can see that's the output. Eta square, descriptive, homogeneity, and O power. Criteria, alpha 0.05 is our significant level. Design equals A, so which you have a single factor is called A. Okay. So that's that. Okay, so this just go through this. And then if you run this syntax, you'll get some outputs, which I'm about to show on the screen. So if you just select and run. Okay, so this title, this output is called univariate analysis of variance. Again, if you want to access to this data, you have to double click it. And then you have you still don't know whether you have selected the data or not. If you click into it, it gives you all these values. It's just very confusing to navigate through the output. But usually we just look at it. That's what we do. Going back to the PowerPoints, because those are easier to see. The first bit is the descriptive statistics. It gives you mean or standard deviation. That's straightforward. And also, you can see the Levene's test of equality of error variances. This Levene's test is a test of homogeneity of variance across the 4 groups. Before, remember, we did the test across 2 groups. And now it's doing it across 4 groups. Again, if it's not significant, that means that there is equal variance. So we can continue. This is the main results that you will be looking at. It's called test of between subjects effects. You can see compared to what we did in there, you can see that the main findings are there. If you compare this to the Excel file that we had earlier, okay? In the Excel file, we have this little table here. So if we compare these two, we show that a lot of values are the same. The mean square for A, for example, A has a sum of square of 49. We have 49 here. The error has a mean square of sum of square of 61. We have 61 here. So that's fine. And the error, it doesn't really specify what the error is, but this we know that it's called subject nested within levels of A. But it also has something else. It's called corrected model. It's the whole model. But that's when you have a general linear model. It gives you all the model data. Intercept. What the intercept does here, the test of intercept, you can see there's an F value attached to the intercept, and there's a significance. It's a p-value attached to the F-test. What it does is it tests the grand mean against 0. So what that test actually tells you is the grand mean 4.25 is significantly different from 0. Okay, doesn't really show what the intercept is because we didn't ask for the parameter estimates, but that's what it does. Okay, so the intercept is something that you basically ignore because I'm not interested in whether 4.2 is different from 0. Right? But you'll be just looking at A, the results for A. You can see that it has sum of squares, degrees of freedom, mean square, F value, which if you check it against the results we got in Excel, you'll notice that they're the same. The significant value here is at 0.001, but we know that's not very accurate. The exact one should be 0.0078, so it's smaller than 0.001. It gives us partial eta squared, 0.445. Again, you have to look at the one that for A, not for intercept, not for corrected model. Non-central parameter, that's the Z-test, I think. And it also gives you observed power 0.97. So what that means is that if you replicate the study with the same kind of sample from the same population, same sample size, there's 97% of the time you will be able to get a significant F-test. Okay? So that's that. Now, here's something that's important before we wrap it up. So what the F-test tells us in the case of ANOVA in our design is that there's an omnibus effect, right? So F-test is usually considered as an omnibus effect, suggesting there's some kind of the four means are different from each other. But again, in order to know whether there are differences between any pairs of these means, remember we're interested in whether intervention 1 is different from the control, right? So we'll have to follow this omnibus test up with some contrast analysis. So a contrast is just a comparison between two means, and you can have it a priori. So it's planned ahead of time, so to test specific hypothesis, or you can do it post hocly or a posteriori, so that you basically explore what differences are out there. Now, there are multiple types of post hoc tests available. Some of them uses t-test, and actually, when it comes to sample means, usually people use t-tests. There's the most simplest form, is called students multiple t. It's just basically running a bunch of t-tests between two sample means, like the way that we have described earlier. But the difference is that the standard error for the t-test is not the same as standard error. It's estimated from the mean square error. But there are also other types of tests. But there are two tests. There's one test that I want you to pay attention is called the Bonferroni test. So this kind of test would adjust alpha error rates based on how many comparisons you'll be running. The argument is that if you have an alpha rate of 0.05, then if you run 4 tests, then you are inflating the alpha rate because by chance the result of the test being significant has been timed by 4 when you run 4 separate tests. So what the Bonferroni method does is that if you want to run 3 tests, then if you want to run 5 tests, right, 5 comparisons, then it would adjust the type 1 error rate by dividing the alpha by 5, by number of tests that you're running. So each test becomes, you have to be significant, not when p equals 0.05, but when p is smaller than 0.01. So it becomes much more difficult to reach significance. So it adjusts for, so the more tests that you run in the same analysis, the more difficult, the more strict it becomes if you use Bonferroni method. Okay, so that's test that adjust alpha rates. So again, this is because that if you run 100 tests, then by default there will be a lot. There will be quite a few of them will be significant by chance. Right? But Bonferroni is a very, very, how do I say, strict or very tough test. So a lot of people just use the multiple t like LSD without adjusting any type 1 error rate. So to include the posthoc test in the ANOVA, all you have to do is to add a line after the EM means. Let me just show you what we had already, and we just have to add a single line behind the EM error, the EM means, to run in order to produce the give you the results of the test. So here's the syntax that we had, and so we have this line called EM means, which is short for estimated marginal means. So if you just say compare after table A, right? Because we have a single independent variable. If you say compare, and run it, now again the results are the same, and then until it gives us what they call estimated marginal means, and then it says pairwise comparisons. Okay, so now you have the results of pairwise comparisons. So let's look at it more carefully of what it is. So you have intervention 1 here, and then you compare it to J. So what it does seems to be is it says here, it says mean difference I minus J, which is basically the t-test, that's the mean difference. And that's the standard error of the t-test, which again is estimated from the mean square error of the f-test. So all the comparisons share the same standard error, and the t-value is just the mean difference divided by standard error, right? So it gives you a significance value of all the comparisons possible against intervention 1. So this is 2 against 1, 3 against 1, and control group against 1. On the right-hand side, it gives you a 95 confidence interval for difference, which you already see in the t-test. it also says whenever there's a star, if you can see at the bottom of the table, whenever there's a little star of the asteroid here, it will say that it indicates that the mean difference is significant at the 0.05 level. Okay? So now we can see that, okay, not only we know that overall the means are different, but it seems that the intervention 1 and the control group, again, looking for p-value, we'll be looking for the column called sig dot. It's called significance value, but these are just p-values. It seems that intervention 1 and the control group has a p-value that's smaller than 0.000001, suggesting that, okay, the intervention 1 is significantly different from the control group. And we can see that the mean is lower than the control group, which means that our interventions has lowered the evaluation of the RP received pronunciation speaker. Again, this is completely fake data. It's just for the demonstration. So intervention 2 also seems to be significantly different from the control group, right? But you can also see that intervention 1 and 3 is not really significantly different from intervention 2. So now at the control group, we can see that it is significantly different from all three other group means, right? Indicating that all 3 interventions are effective in terms of changing the rating of the speaker. Now, what happens if we use the Bonferroni method, right? Go back to the syntax here. If we add adjust Bonferroni, I think that's the case. I'm not, my syntax has been rusty. Let's see if we run it, if we add ADJ Bonferroni to it, what would happen? Okay, so we have our test. What I would do is I will put these 2 tests side by side, the results side by side, to show you the findings, how they're different. Not that easy because there's a lot of things between them. But let's see, like this is what with Bonferroni adjustment, you can see at the bottom of the screen, it says adjustment for multiple comparisons, Bonferroni. And we have run a lot of comparisons here, right? We have run 16 comparisons here. What it does is that it changes the significance value, its p-value, by times the p-value that we got from the previous comparison, time it by 16, I believe. So each t-value has been timed by 16. You can see that the previous p-value for previous p-value for the t-test between intervention 1 and intervention 2 is 0.5, and intervention 1 and 3 is 0.1. But since we adjusted for Bonferroni method, it has become 1. The p-value has, for the second contrast, has become 0.6. Okay. Okay, it timed it by 6 instead of 1. So it has the p-value, they timed the p-value by 6. So you can see that some of the comparisons are still significant, such as the control group versus intervention 1. After, even if you time the p-value by 6, it's still significant. The p is still 0.001. But the difference between control group and intervention 3 the p-value has become 0.06, so it becomes no longer significant after you time it by 6. Now I get it. The reason that it timed it by 6 is the maximum amount of contrast that you can have with 4 groups. The maximum amount of non-redundant contrast you can possibly have with 4 means is 6. So it just timed it by that. So you can see that Bonferroni methods has make the p-values, well, in effect, larger. So it's less likely to become significant because you're running a lot of tests. So it's trying to account for the fact that if you run 6 tests, then the likelihood of getting the alpha rate, let's say that way, type 1 error, is inflated by 6 times. So the Bonferroni method is just trying to adjust for that. It doesn't show it's multiplied by 6, but you can see the same kind of value of the same test, right? So intervention 1 and intervention 3. In the Bonferroni method, after you use the Bonferroni adjustment, it's 0.608. Before any adjustment is 0.101. Okay? So I figured out it's timed it by 6. So the control group with intervention 3 is 0.011 without any adjustments. Now it's 0.068 after adjustments. Okay? So this is it for this week. I think we don't have time to go through another analysis that includes 2 variables, so I'm going to leave it because that's a little more complicated. If you have 2 independent variables, you'll be dealing with interaction effects. So I want to leave that to the next lecture on Monday, on June the 15th. So we will also be going through the case QQ, which is correlation analysis and multiple regression in the next lecture. Okay, so this is it. I'm going to pause recording, and if you have any questions, I'll be hanging around, but I have to sign out before 4 o'clock. But if you have any questions, feel free to pop it on the chat.